Hi everyone, my name's Brendan. Today I'm going to be talking about the KdV equation and soliton theory. I'll shorten it as KdV for ease of talking. So what we want to ask ourselves is, how did the KdV equation develop? The following journal article from Taylor and Francis will be discussed. So Diederik Korteweg and Gustav de Vries, they produced a manuscript in the Philosophical Magazine in 1895, and this was quite historically significant. To put this in context, we need to examine the developments in the field from 1834 until 1895. Now, in 1834, a man by the name of John Scott Russell observed a boat being pulled along a canal by a pair of horses. And what he was describing in his notes, he called it the wave of translation. And we now know that today as a soliton. And I'm going to read some of his notes. I was observing the motion of a boat which was being rapidly drawn along a narrow channel by a pair of horses, when the boat suddenly stopped. Not so the mass of water in the channel which it had put in motion. It accumulated around the prow of the vessel in a state of violent agitation. Then, suddenly leaving it behind, rolled forward with great velocity, assuming a form of a large solitary elevation, a rounded, smooth, and well-defined heap of water, which continued along the channel without change of form or diminution of speed. So this picture here wasn't taken in 1895, it was taken in 1995. This illustrates the idea that he was talking about. And this picture was taken near Heriot-Watt University. So after this, he became quite enlightened about his findings, and he did a lot of water tank experiments after that. And what he observed was that he found that the velocity of the waves depended on its amplitude. And then he came up with a proposal that without viscosity, the soliton would retain its shape for all time values. Now, these following equations provided evidence against his view. So equation 2 here is just the solution of the first, where f is an arbitrary function. And this equation illustrates that a wavefront would become successively steeper until it broke down. Now, as we can see here, as time increases, the wave starts to lose its shape. Indeed, if I zoom in here, it's not even single valued for large values of t. So this equation here didn't support Russell's findings. So there was a bit of a deadlock and a clash of ideas, and some sort of breakthrough was needed, and it was provided by Korteweg and de Vries. So what they did was that they derived equation number 3 here, which has a dispersive term, which acted as a counterbalance to the nonlinear term. And this was quite important. So Joseph Busenek and Lord Rayleigh had earlier provided significant research into this area. and this dispersive term, what dispersion is that it's the tendency of a wave to spread out. So the KdV equation, it's a nonlinear partial differential equation, and it models waves on shallow water surfaces. So we're not interested in waves on the beach, floods, waterfalls, fast rivers, etc. And one quite common form is equation number 4 here. This constant 6 here is just for convention purposes. There's a lot of types of form. There's a lot of different forms of this equation, but usually it's just the constants can be slightly different. Now this second term here is the nonlinear term, and the third term is the dispersive term. And the characteristics of it, it's actually regarded as a very good example of a nonlinear PDE where the solution can be exactly specified. And back here, u is a function of two variables, space x and time t. So analytical and exact solutions exist. And how do we get to solitons? Well, they come from the solution of the KdV equation, and this will be discussed in the proof section of these slides. Now, it's very important for developing and understanding concepts used in nonlinear physics, and it explains one method of providing nonlinear excitations to a system. This is in contrast to perturbation theory, which is a different type of excitation. So solitons, as I mentioned earlier, they come from the solution of the KdV equation. And in terms of chaos or order, they tend to play an orderly role, and this is because they're very resistant against perturbations, and they're also the balancing between the dispersion and nonlinear effects. After 1895, general interest sort of waned. It was quite significant at the time, but not much was. There wasn't much breakthrough in the field until 1965. And in 1965, Zabriskie and Kruskal discovered the soliton. And what they actually discovered was two things. Was that it could be generated through quite general initial conditions, and also that solitons would hold their shape when colliding with another soliton. Yeah, so this was another huge breakthrough, and one of the main ideas behind this was that the KdV equation was integrable through an inverse scattering transform. And what the soliton did was that it allowed weakly nonlinear wave theory to develop and be understood a lot more. So now for given initial conditions governed by the KdV equation, a finite number of solitons are produced. So now we get to the proof section. So we start with this form here of the KdV equation. You'll notice here that the 6 isn't in the second term or the nonlinear term, but there's a kappa here. This is the main idea of the KdV equation is that it's got these derivatives are all in this form with a u here. Yeah, so I've got kappa here, but sometimes the constants can shift around. So we're starting with equation number 5 here. So what we do is that we seek a travelling wave solution, which is equation 6. This is where z equals x minus ct. Now put g of z into equation number 5 on the previous slide, and we get equation number 8 here. Integrate to get 9. We multiply through by g dash to get 10. Integrate again to get 11. And we solve, so for 12 we solve for g to get from 11 to 12. And now with 12 here, we're just going to focus on the positive root, and we're going to let beta less than alpha in equation number 14 here. So we're going to let P of G have the form of equation number 14. To get 15, we're letting G be between beta, so G is greater than beta but less than alpha, and that allows us to get from equation number 12 to 15. We integrate, and here omega is a half, that power there. So we integrate 15 to get 16. And comparing 16 with 13 and 14, we get 17. And now after 17, we get equation number 18 here, where this is with my initial choice of the KdV equation, it looks like this. In general, it'll have this form. Some of the alphas and betas, the overall style is similar, but it is slightly different because there's more than one KdV equation. This sec term here is the main idea of all this. Now this equation number 18 here, this is called a soliton, but it's important to realize that a soliton is just a type, so a special type of solitary wave. So sometimes the terms are used interchangeably, but arguably they shouldn't be, because even though a soliton is a type of solitary wave, they have different characteristics. So more history of the soliton. Now for this KdV equation again, and here we have the constant 6 with the nonlinear term. We get the following soliton solutions. So we get U equals A sec squared gamma x minus Vt. So that's a more general form. And that's got basically the same, looks very similar to this here, this equation number 18. But this was a slightly different KdV equation with the constant 6 with the nonlinear term. So we get this here, and the wave number is gamma, the speed is v, and the amplitude is a. And x is space and t is time. Now there's the following relation. So v equals 2a equals 4 gamma squared. And if you remember earlier with John Russell, he was observing that the velocity of the wave depended on the amplitude. And we see that here with v equals 2a. So what this describes is positive wave pulses, or a family of positive wave pulses. So the larger waves would are thinner and travel faster. And you can see that through equation number 21. So we'll describe a soliton formally here. We've already gone through how to derive it. So a soliton is a large amplitude excitation with a well-defined width. And they maintain their shape after propagating long distances, as well as after emerging from interactions with other solitons. We got an image here. So with the first graphic here, there's a larger, thinner soliton that's behind the smaller, broader soliton. And as time increases they collide, but with the fifth panel here, the longer, thinner one and faster one has overtaken the slower one, but it emerges from the collision intact as we suspected. So even though there's a collision here in panel number 3, the solitons retain the same properties after the collision. So it's a really important observation that the collision did not result in any smaller waves or oscillations. And the two solitons look the same after the collision as they did before the collision. So what are some modern day applications? Well, it's actually, the KdV equation was groundbreaking at the time, and then the soliton theory in general was groundbreaking as well. And that was a huge advancement in describing weakly nonlinear waves in many, many fields of physics and engineering. Huygens principle is one well-known example. And as I mentioned earlier, there are many, many variations of the KdV equation, and there are similar equations. And the reason behind this is that the properties of the KdV equation are characteristic of a family of exactly solvable systems. So here's some more applications. Domain walls in ferromagnets have a solitronic shape. Indeed, many magnets relate heavily to soliton theory. Many biological molecules, DNA is a big one. It has many applications in the field of optics. The propagation of nonlinear acoustic waves in bubbly liquids. Magma flow, so it's got many geophysics applications as well. So Jupiter has a great red spot. So whenever you look at a picture of Jupiter, it's a pretty visible distortion of the atmosphere. And this relates to soliton theory as well. And systems which are wave-like in nature in general, especially involving water and light, have many applications as well, relate heavily to this field of study. So, in conclusion, the development of the KdV equation and the associated theory has so many applications that it's widely regarded as the pillar of nonlinear physics. So the KdV equation was discovered in 1895, and then 1965 was when the soliton was discovered, and that soliton theory really was quite important at that time, and still is today. So interactions between components are vital for understanding most physical systems, and the associated excitations cannot be treated as small perturbations, where perturbation theory would not explain the soliton solutions given here. Thank you for listening, and have a good day.